Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be answering question 2.2 of section 1. So let's begin. This question asks us to show that for a homogeneous ideal, the following are equivalent. Its projective vanishing set is empty. Its radical is either S or S plus, where S is the polynomial in n plus 1 polynomial ring over k in n plus 1 variables, and S plus is all forms greater than 1. And finally, it contains all forms of degree d for some d greater than 0. Now, firstly, the homogeneous Nullstellen sets, as proved yesterday, states that this is an equality Now, the intersections might seem interesting, but if you go back, it assumes that everything is with well, it just tells you that you're only considering functions of degree greater than 0, which it just tells you not SD, S plus. Now, if the projective vanishing set of I is equal to the empty set, then I of v of I is equal to, well, it's all functions such that f of p equals 0 for all p in the empty set, which is S brackets or S plus. Now, as we're intersecting with S plus, then we must have the radical of I intersect S plus equals S plus. As in, this contains S plus, this equals S plus. So, we have an ideal containing S plus. Which ideals can contain S plus? Well, you have either S plus, or you have some ideal which contains S plus and S minus S plus, which is S0, of all forms of degree 0, which just so happens to be K by definition, which is a unit, and as soon as an ideal contains a unit, it is no longer proper. Therefore, the root of I, or the radical of I, is S or S plus. Hence, we have 1 implies 2. I forgot to write here. 1, 2, 3. So we have 1 implies 2. Now, we want to show 2 implies 3. So, suppose I is a homogeneous ideal suppose I is a homogeneous ideal or homogeneous ideal. I still don't know what the correct pronunciation here is. Such that square root of I equals S. Well, since S0 is a subset of S0, but it equals here, we must have I contains S0. Essentially, well, 1 is within the radical of I, therefore 1 to the q is in I for some q, which requires I equals S. Now, S contains SD for all D greater than 0, so for some D greater than 0 as well. Now, suppose I is a homogeneous ideal with its radical being S plus, not SD. It's called the irrelevant ideal, but I am going to call it S plus because we've not been introduced to that yet. Now, then it contains x0 to the q, x1 to the q1, x2 to the q2, dot dot dot. Now, define some capital N to be the maximum over I of the minimum over D such that x to the I to the D is in I. D is within the natural numbers, and then I equals 1 to n. This exists because for each xi there is some natural number. So this is somewhere within the natural numbers. What we want to do is to consider some monomial within... Oh, a monomial is of the form x0 to the e0, x1 to the e1, dot dot dot, xn to the en. Some monomial in S, some monomial of degree n multiplied by n, big case N multiplied by little case n plus 1. Now, e0 plus e1 dot 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 plus en is by definition going to be n multiplied by n plus 1. So, I believe it's called the pigeonhole principle, but one of these numbers must be at least n, because otherwise you're having n plus 1 numbers, each less than n. Therefore, this must be a strict inequality to the left, but it must be a strict less than if this is not the case. Hence, m is divisible by xj, let's say, to the big N for some j equals 0 to n. This implies that m is within I because x0 to the n, comma, x1 to the n, comma, x2 dot 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 to the n, x lowercase n to the capital N are all in I, and I is an ideal. Therefore, I contains all forms of degree big N multiplied by lowercase n plus 1. In other words, 2 implies 3. We've already got 1 implies 2, now we have 2 implies 3. Now, oh goodness. Now we must only show 3 implies 1. So, assume that I contains S to the D for some D greater than 0. Consider some point I'm going to use colons instead of commas, P2, colon, P0, P1, P2, dot, 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 Pn. Now, because we are working in homogeneous coordinates, at least one of our pi's is non-zero. So, choose some pi non-zero. Xi to d is within our ideal. So, f equals f equals xi to the d vanishes on p. F of p equals pi, which is by definition non-zero, so contradiction. Therefore, the vanishing set of our ideal, the projective vanishing set of our ideal, is empty. And 3 implies 1. Now, we've shown that 1 implies 2, which then implies 3. So 1 is equivalent to 3, and then the same for each of them. We've actually, if you've never seen something like this before, we've built a directed graph where you can start at any point and finish at any point. So we are done. QED. So, as always, thank you for watching. Okay, goodbye.